In this video, we're going to be going through section 8.1, the second homework assignment in the section, and that is on page 423, numbers 1 through 2, 5 through 12, and 17. So number 1, it says, what is the U-shaped graph of a quadratic function called? And that answer there is parabola. It's called a parabola. All right, the second question here, number 2. It says, when does the graph of a quadratic function open up? So the parabola would look like this. And when does it open down? So the parabola would look like that. So there's two instances, one where it opens up and one where it opens down. It will open up, let me type this one out here. Oh, that's too big. Let's go with this guy. A parabola will open up if the leading coefficient is positive, and it will open down if the leading coefficient is negative, and that is that A value. So remember, give me a second to adjust this. So remember, all of these equations, all of these quadratic equations can be written in the form y equals ax squared plus bx plus c. And if A, this value right here, if the leading coefficient A is negative, then you get that reflection over the x-axis and the parabola would open down, otherwise it opens up. All right, the next one is number 5. On numbers 5 through 12, you have to graph the function and then compare the graph to the graph of f of x equals x squared. So on number 5 here, we're going to graph g of x. Okay. So we're going g of x equals 6x squared. All right, so to do that, just like I showed in my lesson, we can just make an input-output table, xg of x. If you know those transformations really well, you could just see that this is a vertical stretch by a factor of 6 because our a value is 6. And then you could, instead of graphing the points on the parent function like 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4, you could graph the heights 6 times as tall. So you could graph 0, 0, 1, 6, 2, instead of 2, 4, you'd have 6 times 4, so you'd have 224, and then all of the points on the other side of the y-axis. So you could use the transformations, but again, you can just make an input-output table, that's all right. So I'm going to plug in some values here. I'll plug in 0. Follow the order of operations, so square your value first and then multiply by 6. So 0 squared is 0 times 6 is still 0. If I input a 1, 1 squared is 1 times 6 is 6. And if I input a negative 1, I'd get negative 1 squared, which is positive 1 times 6 is still 6. I could try to input a 2. If I input 2, I'd get 2 squared is 4 times 6 is 24. And negative 2 would also give me out a 24. So if I want to go to graph this, I'm not going to adjust my intervals on my y-axis. I'm going to graph 0, 0, 1, 6, negative 1, 6, and then 224 or negative 224. I'm not going to cross x equals 2 on this graph because 224 or negative 224 are way above the graph, so I'm not going to cross x equals 2 or x equals negative 2 when I go to graph. Now again, I'm doing this with a mouse, so this is going to look pretty terrible. I'll try my best here. That's not too bad. All right, and this is the graph of g of x. All right, so it does say also for 5 through 12 that we have to compare to the parent function. Now, I said this verbally already, but I do want to write down my answer here. So compare to the parent function means list out those transformations compared to the parent function. In this one, I suppose I should make the point here again. The parent function is the parent function for this family of functions. The family of functions we are dealing with is the quadratic family because we have an x squared, and that is my highest degree. The parent function is y equals, or f of x equals x squared. That is the parent quadratic function, the most basic function in the quadratic family. So the only difference with this function compared to the parent function is that I have a 6 as a leading coefficient instead of a 1. So that is why this is a vertical stretch by a factor of 6. And again, you can just list out the transformations. So if there's more than one, you just create a list and we'll list them all out. So that's number 5. All right, so keep on going. In number 6, we have to graph b of x equals 2.5x squared. So this is very similar to the last one. This one, the leading coefficient again is above 1, so this is a vertical stretch by a factor of 2.5. And again, we are just going to make an input-output table to get the coordinates to graph. So x, b of x. I'll start by inputting a 0. I'll also input 1, -1, 2, and -2. Alright, so if I input 0, follow the order of operations. 0 squared times 2.5 is 0. 1 squared is 1 times 2.5 is 2.5. You get the same thing out with the -1 inputting into the function. If you plug in 2, you get 2 squared, which is 4. 4 times 2.5 is 10. And if you input -2, you also get a positive 4 times 2.5 is 10. Alright, so graph these points. I have 0, 0, 1, 2.5, just approximate between 2 and 3. -1, 2.5, 2, 10, right at the top of my graph here, and -2, 10. So again, all of these graphs, because they are quadratic functions, should be parabolas. They should all be U-shaped. So if you get anything other than a U-shaped graph, you know that your work for when you input the values and got out the outputs, you know that some of those are incorrect if you don't get that perfect U shape. And there we go, this is b of x. Alright, so one more time, I said this already, but I need to type out my transformations. So this is, because it is the leading coefficient is a 2.5, I'm going to say that this is a vertical stretch by a factor of 2.5. And you might notice that all of my y coordinates are 2.5 times as big as the y coordinates on the parent function. And that makes sense that it's a vertical stretch because all my y coordinates are 2.5 times the distance from the x-axis. All right, moving on to number 7. In number 7, the leading coefficient is no longer greater than 1, it's between 0 and 1. So this is not a vertical stretch, but rather a vertical shrink by a factor of 1/4. I'm just going to type that out right away here. So a vertical shrink by a factor of 1/4. That is my only transformation on this one. To find my points, again, I'm going to make an input-output table. So x, h of x, and I'm going to input 0, 1, -1, 2, -2, 3, -3. Now, the heights that I expect to get out of here, the y coordinates or the h of x coordinates, the values I expect to get out are all going to be 1/4 as big as the parent function y coordinates, which makes sense because we're inputting the same x coordinates that I input into the parent function in my lesson video, and then we're going to take all of those and multiply them by 1/4. So all of these are just going to be 1/4 as big as the parent function values. But let's do this anyway. So input 0, you get 0 times 1/4 is 0. Input a 1, you get 1. 1 times 1/4 is 1/4. Input a -1, turns into a positive 1 when you square it and multiply by 1/4, you get 1/4. Input a 2. 2 squared is 4 times 1/4 is just 1. Input -2, you also get out a 1. Input 3, you get 9 times 1/4, so 9/4. I could write 9/4, but ultimately 9/4. It's going to be easier to graph if I write this as a mixed number. So 4 goes in 9 twice, and we have 1/4 left over, so 2 and 1/4. And if you input -3, and when you square it, you get a positive 9 again, times 1/4 is again 2 and 1/4. Alright, so let's go ahead and graph these points. I have 0, 0, 1, 1/4. Again, just approximating, going up 1/4 of the way. I've got -1, 1/4, 2, 1, negative 2, 1, 3, 2 1/4, negative 3, 2 1/4, and I still have a lot of space on my graph up here. Now, if you drew a sketch, you might have just changed your y-axis or maybe made your tick marks a little bit farther apart, and that's fine. But since I have so much room, I'm going to just plug in one more here. Let's go 4, negative 4. So if I plug in 4, I get 16 times 1/4, which is 4. And negative 4 is, again, 16 times 1/4, which is 4. So 1, 2, 3, 4, 1, 2, 3, 4, and negative 4, 4. And again, it should make that U shape because all of these quadratic functions have parabolas as their graph, and that means that they are U-shaped. So it does look U-shaped, so that tells me my work is most likely correct, and this is function h of x. All right, moving on to number 8. Number 8, this is a very similar problem to number 7. The leading coefficient is 0.75 3/4 instead of a 1/4. So I'd expect my heights to be 3/4 as much as the parent function, where these were just 1/4 as much. All right, so let's go ahead and make an input-output table, xj of x. And one more time, I am going to plug in those values, 0, 0, 1, negative 1, 2, negative 2, 3, negative 3. I'll start there. Let's see what my graph looks like. All right, so 0, if I plug in 0, square it, and multiply, I get 0. So I'm going to start speeding up on these input-output tables, so I don't have to say all my work. I'll just show you the values I'm getting out. Let's plug in 1, I get 0.75. 2, I get 4 times 3/4 is 3. Get the same thing here as when I plug in positive 1. Same thing here as when I plug in positive 2. Plug in 3, I get 9 times 3/4, which is 6 3/4. And then I get the same thing plugging in negative 3. All right, so going to graph those. 0, 0. 1.75, again, just approximate 3/4 of the way up. Negative 1 3/4, or negative 1.75. 2, 3, negative 2, 3. 3, 1, 2, 3, 4, 5, 6 3/4, and negative 3, 6 3/4. And again, it should be that parabola, that U shape. So this looks good. And this is j of x. And to list my transformations on this one, that leading coefficient is between 0 and 1, so this again is a vertical. I might as well just copy the one I put right here. This is a vertical shrink by a factor of, oh, it's not going to let me change that, by a factor of 0.75, or you could say 3/4. So vertical shrink by a factor of, I'm going to use 0.75 since it says 0.75 is my leading coefficient. All right. Let's keep moving. So number 9. On number 9, this is the first one you see with a negative leading coefficient. Also in numbers 10 and 11 and 12. So the remaining 4 problems all have a negative leading coefficient. And as we talked about up here, on problem number 2, a parabola will open down if the leading coefficient is negative. So we'd expect all 4 of these other graphs to open down. All of the first 4 had positive leading coefficients, so they all opened up. So that's another transformation that helps you know if your graph is correct. All right, so let's go ahead and make the input-output tables for all of these. There we go. Input-output tables made. Little movie magic. So don't forget, when you plug in your values for x, you need to follow the order of operations. So you have to evaluate the exponent first and then multiply. So I'm going to go ahead and do that. And they're all filled in. All right. So next up, we do need to graph all of these points. So I'll go ahead and do that. And then draw the graph through the points. And that's what it looks like. So notice on this one, I've got negative 3, negative 18, and 3, negative 18, which are off of my graph. So I didn't need to use those 2 points on this one, unless, of course, you changed your interval on your y-axis. But as expected, this one opens down, and the distance from the x-axis is twice as big, just like we expected. So thinking of those transformations, with the parent function, you would have the points 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, and negative 3, 9. That's the parent function. So that's not actually our graph. That's the parent function. That would be f of x equals x squared. And on this one, notice this point is right at the origin, so you're on the x-axis. So stretching 2 times away from the x-axis, when you're on the x-axis, it doesn't go anywhere. But this point is 1 unit away. Well, now, this point in our new graph is 2 units away, twice as big. But because it's a negative 2, it's below the x-axis, and it's twice as tall away from the x-axis. This point was 4 units away. But now we're 2 times that distance, so now we're 8 units away from the x-axis with the point on the graph. This point was 9 units away, but now we're 2 times that, so we're 18 units away, so we'd have to go down to negative 18. So again, using those transformations, we really could have skipped building the input-output table, and we could have just, thinking of those points in the back of our mind, 1, 1 would go 1, negative 2, because it's twice as tall. And it's negative, so it's below the x-axis. Instead of 2, 4, we'd go 2, negative 8, because it's twice as tall. So instead of 4 units, you go 8 units, and we go down because it's negative. So that's just a little shortcut in graphing any one of these functions in the form y equals ax squared. All right, let me get rid of that. And then we'll continue on with the transformations. So we still have to list out those transformations. So on this one, we've got, because of the negative a value, that's causing a reflection, and the 2 is still causing a vertical stretch or shrink. In this case, it's greater than 1. The 2 is greater than 1, so this is a vertical stretch by a factor of 2. And yes, we do still say by a factor of 2, not by a factor of negative 2. The negative is separate, that causes the reflection, but we're still twice the distance away from the x-axis. That's why we say it's vertical stretch by a factor of 2, meaning twice the vertical distance as the parent function. All right, so that's one of them. The other one, as I mentioned, is a reflection, because of that negative a value, instead of opening up, it now opens down, so it reflected over this x-axis. So a reflection over the x-axis. Remember, you do always have to say which line you're reflecting over, so you have to include that you're reflecting over the x-axis. All right, moving on to number 10. I'm actually going to go ahead and graph all of these real quick. One note about numbers 10 and 11 before I do that. On this one, I plugged in 2 and negative 2, and I got out negative 18, so I'm already off my graph here, so I didn't even plug in 3 or negative 3. In contrast to number 11, when I plugged in 3 and negative 3, I was still really close to the x-axis, so I continued on. I plugged in 4 and negative 4, and I'm still pretty close to the x-axis, so I kept going. I plugged in 5 and negative 5. Now I'm a little bit farther away. If I were to plug in a 6, I'd get 36 times 0.2. 36 times 0.2, and that's a negative 0.2. I can't find my negative button right here. Here we go. So negative 7.2. So I could also plug that one in as well. But ultimately, I just want you to plug in enough points so you can really see that parabola shape forming, that U shape forming. You don't just want to have points really close to the x-axis, because then it's hard to understand what happens farther out on your graph. But the other ones, I was the last one, I should say, number 12, I was able to just plug in negative 3 up to 3, and I'll be able to tell what my graph looks like pretty good from this many points here. So again, I'm going to go ahead and graph all of these, and then we'll talk about transformations. All right, so let's discuss those transformations. So on this first one here, on number 10, I have a negative leading coefficient and then a 9/2 in front of that x squared. So my leading coefficient is a negative 9/2. If you simplify 9/2, or I should say if you convert it into a mixed number, that's 4.5. So just like the previous example, that leading coefficient, if you take the absolute value, that's greater than 1. So that is again going to cause a vertical stretch. So this is a vertical stretch by 9/2, or you could say a vertical stretch by, let's say vertical stretch by a factor of 4.5. And one more time, it is supposed to be a positive because we're 4.5 times the distance from the x-axis as the parent function would be. And then we also have a reflection over the x-axis because our leading coefficient is negative. And that causes it to open down instead of opening up. like the parent function. On number 11, again, that negative is the same. So again, we have a reflection over the x-axis, so it's opening down. Our leading coefficient, though, if we take the absolute value, is a 0.2, which is not greater than 1. So this is a vertical shrink by a factor of 0.2. So it's 0.2 the distance away from the x-axis. So we're closer to the x-axis than the parent function for the heights or the y-coordinates or the k of x coordinates. And then this is a reflection over the x-axis because of the negative leading coefficient, and it causes it to open down. And then for number 12, for the last one of these graphing problems here, this is 2/3 is between 0 and 1, so this is a vertical shrink by a factor of 2/3. So we're only 2/3 the distance away from the x-axis compared to the parent function, and the negative causes it to open down, so this is also a reflection over the x-axis. So a lot of those transformations are the same throughout a lot of these graphing problems on this assignment. Last question, number 17. Describe and correct the error in graphing and comparing these two graphs. The blue graph is y equals 0.5x squared. The black graph is y equals x squared. So down here it says the graphs have the same vertex. Remember, the vertex is just the highest or lowest point. In this case, they both have a lowest point, so that's correct. They have the same vertex and the same axis of symmetry. The axis of symmetry splits the graphs in half, and yep, the y-axis splits both of those equally in half. So that first sentence is good. The second sentence says the graph of y equals 0.5x squared is narrower than the graph of y equals x squared. Well, based on the picture, that is correct. So that second sentence looks okay. But are these graphs correct? So maybe how they graphed them is the error. So let's see. If the leading coefficient is a 0.5 or 1/2, that should be a vertical shrink by a factor of 1/2. So if that's the case, if it's a vertical shrink compared to the parent function, these points should not be taller compared to the black graph. They should be shorter. So that blue graph should actually be coming down here, and it should be something like this, only 1/2 the height as the parent function. So that is what is incorrect. Their graph is incorrect. So I'm going to say they did not correctly graph y equals, because I can't put a squared in here, I'm going to say they did not correctly graph, no, I'll just have to write this way, y equals 0.5x squared, so that caret symbol means squared. The graph should have been, actually the graph's y coordinates should have been only 1/2 the height of the graph of y equals x squared. Ultimately, this would mean that the blue graph should have been wider, so the graph of y equals 0.5x squared should be wider than the graph of y equals x squared. And I know a lot of you looked in the back of the textbook at that one because your answers, a lot of your answers mirror the answer in the back of the book. It's an odd problem. I don't necessarily blame you, but please make sure you are trying to think through these on your own. But that's my explanation. A little bit different than the back of the book, but so again, they did not correctly graph y equals 0.5x squared. The graph's y coordinates should have been only 1/2 the height of the graph of y equals x squared because of that vertical shrink by a factor of 1/2. The graph of y equals 0.5x squared should be wider than the graph of y equals x squared, and that's essentially what the author said in the back of the book. But there you go. That's the assignment. If you have questions, let me know.